Hi everyone, welcome to the Torque Theory webinar. I'm Jason Benford, and today we're going to talk about bolted joints and what it takes to keep them tight. So let's talk about some of the advantages of bolted joints first off here, because I think it's important to amplify some of those advantages in our process. So it's good to know what those things are. One of the first things I think everybody knows about bolted joints is the serviceability aspect. A bolted joint can be tightened and loosened and retightened. So that's a pretty big advantage compared to some other forms of assembly like gluing and riveting and welding and things like that. For the most part, we have quick and easy assembly, so we can tighten a bolt in a matter of seconds and have it be a secure connection for the life of a product. Bolts can be pretty cost efficient. When you've got a large quantity, we can have a bolt cost, a few pennies and do a huge job of keeping large things together for a really low cost. Bolts have the advantage of connecting different materials. We can attach steel and aluminum where that might be more difficult with a weld or a different type of joining application. Another aspect of bolted joints that's important to consider is that we have standardized elements. So that means I can buy an M10 by 1.5 millimeter thread pitch, that's a 10.9 material strength, anywhere in the world. So the standardization of bolted joints really lends them to when we have global product assembly. So we can have assembly plants in different continents making very similar products in very similar ways, and that standardization is a real advantage. There's another advantage we can talk about the bolt being the weakest link of an assembly. So we can actually design a bolted joint to fail before a more expensive part fails, where that type of idea is difficult to do when we're welding parts together. But if I bolt a plow to the front of a truck, if that plow hits something that's immovable, I could design my joint to fail where only the bolts break instead of something much more expensive like the frame of the truck bending. All right, let's talk about the goal of a bolted joint, generating clamping force. So as we turn the bolt, the head of the bolt or the nut, it's like driving up an inclined plane. So I think everybody can pretty clearly picture tightening a bolt. What we're actually doing with the bolt is turning and going up an inclined plane. So it's a simple machine. So as we turn, it forces the bolt to stretch like a spring. As we travel up that inclined plane, we stretch the bolt like a spring. That spring force is what holds the joint together. The goal of tightening is to generate a consistent amount of clamping force on the part. So I want you to think about a bolt. When you picture tightening a bolt, I want you to picture tightening it like it's stretching a spring, and that resilience of that spring force is what squeezes and holds the joint together. So here's a good picture of what I mean when I say that. So the greater the force we apply, the more that bolt is going to stretch. So we put a large amount of force on a bolt, it's going to stretch, and its resilience is going to squeeze back on those parts. And it's almost like putting a part in a vise. So I think most people have used a bench vise like this, and you can really create a tremendous amount of force by turning the handle of this and squeezing whatever you put in the jaws. Well, the bolt is acting just like this. And this is actually a picture of a bolt that can generate just as much force as a very strong person could put tightening the handle of this vise. So you can get a picture of just how big of a job that small bolt is doing. So let's talk about some basic definitions here. We've got static state, which is where the clamping force and the preload are equal and opposite forces. That I've just tightened this bolt. I got 10,000 pounds of tension force in the bolt, and I'm generating 10,000 pounds of clamping force in the part. So in a static state, those are equal and opposite forces. In a dynamic state, we're going to load this joint with some external forces. That could be anything from a gear assembly being bolted together, or an engine, or an electric motor, or car suspension, or articulating part of a tractor. Really anything that's going to have bolts holding it together is going to have external forces acting on it. And so we want to consider how those forces go into determining the loads in the joint. So we could have a force like this in the axial direction trying to pull the joint apart, or we could have a shear force trying to slide the joint together. This could be like a wheel on a car, right? You tighten up the lug nuts, you apply this elastic force, the tension force in all the lug nuts, and it squeezes the joint together, and the friction between the surfaces is what maintains the bond of this joint. And what holds all the torque that the wheels put onto the road. It's important when we're trying to solve bolted joint problems to understand the forces going in and how the joint is going to handle external forces. So if we look at a simple bolted joint, we have 2 newtons of tension force. We could call this tons of force, pounds of force, whatever we want. But this is a force unit that we're gonna stretch this bolt and apply 2, let's call it newtons of tension force, and it's gonna produce 2 newtons of compression force on the part. But what happens to the bolted joint when we apply an external force to it? So what happens to that tension force in the bolt? And this is the first counterintuitive thing that we come across when we talk about bolted joints, is the relationship between the preload of the bolt and the clamping force in the part. So what actually happens here is that the load in the bolt stays stable. So if we've done a good job in our bolted joint design and gotten the right stiffness properties, we can tighten a bolt and have almost no effect on the tension force of that bolt fluctuating up and down as we apply an external force. So this leads the bolt to be really stable. And this is one of the biggest advantages of a bolted joint, is the preload of the fastener maintains its tightness throughout all of the service load. And this is something that can be a little counterintuitive, but if we look at it from a free body diagram standpoint, we can really get an understanding of the forces. At this point right here, when we've got our service load at 2 newtons of force and our preloads at 2, the clamping force is actually dropped down to 0. So this is the point at which we have a failure. We're going to see a failure of this bolted joint at some point. There's nothing keeping this joint from sliding together. So if you are designing a bolted joint, the first step is to understand the service load and then design your bolted joint and your tightening process around achieving a higher bolt preload than the service load is ever going to be. We can look at this relationship between bolt tension and compression. Kind of repeat this graphic here. We've got 2 units or 2 newtons of tension force and 2 newtons of compression force in the part. As we add service load, it drops the clamping force, the compression force, but not the tension force in the bolt until we get to the point where the service load exceeds the bolt preload. Here we have a problem. 3 newtons of force on the bracket is now alternating my bolt preload from 2 to 3 to 2 to 3. So this is the point where there will be imminent bolt failure. We'll have a fatigue fracture, or the nut will come loose, or something will fail in the joint. So we want to make sure from a design standpoint from bolted joints that we're tightening them a high enough level where we've understood what the foreseeable loads are going to be as our part that we're building goes out in the field and may get abused and have some really high loads on it. So the best scenario is to tighten the bolt to a high and safe level, and that can withstand the service load. So the bolt needs to be tight in order to do its job, and if the bolt's not tight, the part can fail. All right, so how do we tighten a bolt? We tighten a bolt with torque, right? This webinar is called Torque Theory. So the goal is to tighten it in such a manner that we achieve the clamping force we want. So the most common way to do that is with a torque joint. So what we do is we apply a twisting moment onto the bolt, either onto the nut. Usually we tighten the nut if we can, but oftentimes we're tightening the head. And what we're trying to do is apply enough twisting force to generate the clamping force. Just like the handle of that bench vise. As you turn that handle of the bench vise, it squeezes the jaws together. That's exactly what we're doing when we tighten a bolt. So torque is a product of force and distance. And I think that's a pretty comfortable thing most people realize if they look at it like this, is that if I'm talking about 10 foot-pounds, it's like putting 10 pounds on the end of a 1 foot long wrench. If we're talking about SI units, then maybe I'm talking about 50 Newton meters being, half a meter and having 100 newtons of force. It's a product of the force and the distance. So I think it's a pretty straightforward thing to realize that if you need more torque on something, you can either put more force on it or put a longer lever arm, like putting a pipe on the end of the wrench. So torque is how we apply the twisting force to the joint to generate the clamping force. So the longer the wrench, greater the torque. All right, so let's walk through a tightening, the phases of tightening. So let's walk through the, as we tighten a bolt, what are the areas we want to concern ourselves with? All right, so here's our torque versus angle chart. So this is the rundown of a bolt. We have some phases here we're going to break this up into. So here we have the rundown phase, our drawdown where we snug the parts together, the linear elastic region where we're tightening that bolt, and then the plastic region beyond that where we've now over-tightened the bolt and the bolt is broken. So when we look at this graph, we want to break this down into its specific components. So the rundown is just turning the nut and spinning it down. If there's a lock nut or something on there, it's going to have some torque it takes just to run the thing down. But usually that's a pretty low value. Our drawdown phase is where we're starting to clamp these parts together. We're aligning the parts, starting to squeeze them. If there's any parts need to be drawn together, that's what's happening in this phase. In our elastic phase, this is our linear elastic phase where we're stretching the bolt like a spring, and this is where the torque target is usually located. So in almost all cases, we are tightening a bolt within its elastic range. So I'm showing you the whole curve here of actually a failed fastener. So we want to understand that at some point, the torque is going to get so high and the bolt tension is going to get so high that it starts to exceed the strength of the material, and we have this permanent deformation that occurs at the plastic range. And that's really the limit that we can have for strength of the fastener. And there won't be very many fastening processes that go into the plastic range, but the ones that do go in a very controlled manner, only very little amount of plastic range there. So what we're usually looking for is this nice straight linear elastic region where we want to be in our torque value. All right, in this section we're going to talk about how friction affects clamp load. So we have to realize that friction is going to play a role in the relationship between the torque we put into the bolt and the clamping force that the bolt generates, the force that holds the joint together, that actually does its job. So we can see from this pie chart that 50% of the torque that I put into the bolt goes into overcoming friction under the head of the nut or under the head of the bolt, whatever place I'm turning. All right, so if I'm applying torque to the nut, then the face of that nut that's turning against the part, half of my torque goes into overcoming friction there. We also have 40% of the torque going into overcoming friction in the threads. So there's two places where friction is at play, and that equates to 90% of the installed torque going to overcoming friction. That only leaves 10% left over to generate the clamping force that's going to hold this thing together when it gets out into the field, whatever we happen to be assembling. So this relationship is going to create some differences in the amount of clamping force. When the friction changes, the clamping force is going to change. So what happens if we get some contamination with oil or grease on the threads? So we look at the pie chart where we started off, and we find that the thread friction drops the percentage of applied torque to overcoming friction in the threads from 40 to 30%. And that goes directly into dramatically increasing the clamping force on the part. So the bolt preload jumped up from 10% all the way up to 20%. So we doubled the preload. And in most cases, that is too much for the bolt to handle. Most bolted joints are designed to handle somewhat more than 50% of their ultimate tensile strength. So if you have more than double 50% of your ultimate tensile strength, you're going to end up with a broken bolt. And this is exactly how bolts break. And I think we've all experienced this. When you run a bolt down and you're trying to get to a torque value and it turns and turns and turns and turns, but it isn't quite getting there, that's when a bolt breaks, and that's usually due to the friction being too low for the applied torque. So you get this classic hourglass shape. This is just like a tensile test specimen, and that's what most of the force going into this thing is, creating tensile force. So you can see that hourglass shape in this picture, and this is a bolt that has been fractured from too low a friction for the torque that we applied to it. All right, how about damage to the bolt threads? We're looking at the same area, the friction in the threads, but we're getting a different condition. So now this is going to increase the friction from 40% up to 50 or 48%, and now it leaves only 2% left to tighten the bolt. So the small change in friction results in a really large change in clamping force. So what we've got here is high friction causing low clamping force, and this joint is going to underperform when it gets into the field. And for me, this is a more concerning thing than the low friction joint. Because the low friction joints, some of them are going to break, and you're going to know that there's a problem. But if you've got a low friction joint, it's much more difficult to realize that could be happening for every bolt. If you had a batch of rusty parts, it would be more difficult to realize that you were under tightening every bolt. And since it's the bolt preload, the high bolt preload that resists service load and that keeps things tight in the field, low preload is very prone to failure. If the friction's too high, the clamp load's too low. And there's some other things that can affect bolt preload. We can have thread adhesive. This can change the friction. It can change it by lowering it in its liquid state or increasing it if you were to reinstall this after the glue had been cured already. We've got different types of lock nuts. There's a number of different things that can change friction in the joint. And the biggest problem that we see with assembling bolted joints, especially in a production environment, is variation of friction. If you take nothing else from this webinar than to really look at how friction can be different, and whether that's keeping things from contamination or making your bolt coating as consistent as possible, those types of activities should yield very consistent results with the tightening. So the biggest problem with fastening is variation in friction causing differences in the clamping force that the bolt generates. So this is a picture of a failure test. This is 25 samples where we broke these in the laboratory. And so what we do in the laboratory is develop torque specs. And so this is an example of, a pretty big variation, what looks like a pretty big variation in the amount of torque it takes to break a bolt. But really, this is pretty normal, and this is to be expected with a torque control process, is that even within a brand new box of bolts, I would expect to see this level of variation. And most of this, in fact, really most of that we can measure. There are some other factors at play here, but the vast majority of the cause of this variation is differences in friction. I don't want to say too many bad things about friction because friction is a good thing. Friction is what keeps the joint together. It's not about the friction being a problem. It's about the variation of friction causing inconsistencies in the tightness of our joint. Prevailing torque can happen in a couple of ways. And really, prevailing torque is the torque in the rundown phase of the fastening. So this is before the nut seats against the part and we start drawing the parts together. This is just either driving the screw in or just running a nut down. The idea of prevailing torque is just the torque it takes to run down the fastener. So this can occur in a couple of ways. We can have intentional prevailing torque. That would be like a lock nut, like a nylon ring lock nut, right, where you could run down. This could be a sheet metal screw where we're forming and cutting a thread into it. This could be a trilobular fastener where we're driving a steel fastener into an aluminum hole and forming the thread as we're tightening. So these are some examples of intentional prevailing torque. And we can overcome that in the fastening process by designing the right torque for the application. We can also have unintentional prevailing torque. This could be holes that aren't aligned correctly. Maybe the parts are damaged. Maybe the paint, there's too much paint or too much coating, right, or weld spatter in the thread. There's definitely some things that can cause unintentional prevailing torques, which is going to affect the tightness of our joint because it's going to take away from the final tightening. As far as the power tool is concerned, that can change the rundown, right? We could prematurely speed shift and slow the tool down. If we're running like a pulse type of tool, drastically increase the number of pulses we need to tighten. There's some differences in how we're going to see that in a direct drive versus a pulse drive system, but generally prevailing torque applications are going to be a little more wear on the tool, and they're going to take away from the clamping force. We want to make sure we're getting a good quality bolted joint by monitoring the process. And here's a good picture of, the the parts that we're building here. We're just starting to form a thread at the beginning during the engagement phase, and then as we drive in and form more threads, the torque builds up. But we don't actually generate any clamping force until the fastener's fully seated. So any torque that's consumed during that rundown phase is going to take away from the torque that goes into tightening this bolt and keeping it together through its service life. Let's talk about monitoring the fastening process. So the clamping force is the goal, but there's no easy way to measure clamping force as we tighten. All right, there's no good way to actually verify the exact bolt preload. So we can monitor the torque, but what's really keeping the joint together is the compression force, the clamping force that the preload of the bolt generates after it's been tightened. So we can monitor the tightening angle, and that can give us a really good indication of the consistency of the clamping force in the joint. How do we monitor that angle? Once the joint is snug, then we set up our tool to measure how much angle it takes from a snug torque to the final torque. And that's going to be a really good indication of the consistency of the tightness of my joint by monitoring the consistency of that tightening angle. Every joint's going to have a different angle, but we can really use this as a good metric to understand the consistency of our joint. Depending on how long the bolt is, the parts we're going to pull together, you might turn 30 degrees or you might turn 720 degrees to achieve, that torque value that you set for the tool. But the angle and the consistency of that angle is going to be a really important factor. We talk about hard joints and we talk about soft joints. Really what we're talking about there is the amount of angle it turned from snug to tight. For a joint, we're going to set that snug torque at maybe 25% of the final torque. That could be 50% for some applications. You can program that value, within quite a few of our tools. And we want to look at the variation of angle when we talk about monitoring the tightening process. The cause of this variation of final angle from snug to torque is mostly caused by friction variation. So we want to realize that some of that's natural and acceptable, but we also want to realize that if we fall outside of what the normal results are, that's a situation where we want to utilize the features of the tool to reject a bad assembly. So in this situation, we've got a couple of examples. We've got low angle. This could mean we've got a missing gasket. Maybe we have really high friction, and this would be a situation where the clamp load might be low. It might be too low to keep this thing together. On the situation on the right, we've got high angle. Maybe this means that the friction is very, very low and we have too much clamping force and we're on the verge of cracking our part. This could mean maybe we have 2 or 3 extra gaskets in the situation. That's, again, something we want to use to monitor that. So by monitoring the tightening angle, we can put some really simple parameters in place to reject a bad assembly and really get additional value out of how we set up the power tool. So that's a really simple but powerful tool to help ensure we're making a good quality assembly. All right, let's talk a little bit about how joints can lose the clamp load. Anytime we lose the elastic stretch of our bolt, we're going to lose the clamping force. In particular applications where we get heat coming into our part, it can cause the part to expand. And if that happens over and over again, we can see embedment against the part, and what results is a loose bolt. So you'll see a lot of technique involved in things like exhaust manifolds and flanges on high temperature applications, where we really are trying to make sure that the bolt has enough elasticity to handle the changes in dimension caused by the heat cycle. Another form of relaxation is called embedment. When we tighten the bolt down, and this is a result of the tightening, as we tighten the bolt down, we generate thousands of pounds of force, and the microscopic imperfections in between every surface actually form into each other and results in a few milliseconds later, the bolt actually losing its clamp load. So this is an application where going a little more slowly or retightening the bolt can really improve the integrity of the joint. So another way that joints can lose clamp load is from what we call creep. And really this is when the material being put under really high compression flows out of the joint, where we no longer have it supporting the bolt. So the bolt can be tightened and stretched, but over time that material can flow out. This tends to happen with soft materials. We have plastic and rubber trapped in our joint. Then we find that they can get thinner over time, where the actual material will flow away from the joint. This can happen with layered painted surfaces. The time it takes for gasket creep type of relaxation to occur really depends on what the gasket material is made of, but it could take, minutes or hours or days to fully settle out. Those situations we may want to address this from a joint design standpoint to improve the integrity of the joint, but really any situation that results in a loss of the stretch of my bolt is going to lose the clamping force that it generates. So if you lose the thickness of the joint, it's going to directly lose tension force in the bolt and how tightly that bolt is squeezing on those parts. All right, let's talk a little bit about bolt strength here. I want to touch on this because it applies to the torque that we put into the joint. In the metric world, you will see numbers like this on the top of the bolt. These numbers refer to the material strength of what that bolt is made of. What is the tensile strength of this material is what that number defines. If you have an English or an SAE graded bolt, you'll see dashes on it. Three dashes is similar to an 8.8 bolt in terms of material strength, and if you see 6 dashes, that's similar to a 10.9 as far as its tensile strength. So same concept, just a different method of marking it on the head of the bolt. And for this bolt, we see we've got a 10.9. So let's break down this number into its parts. So really 10.9 is 2 numbers here. So 10 is 1/100th of the ultimate tensile strength. So really 10 means 1,000. So that means for every square millimeter of cross-sectional area that this bolt has, it can hold 1,000 newtons of tensile strength. 1 square millimeter is only about the wire size of 1 paper clip. So you can picture that if this were an M10 bolt, it would be made of many paper clips of cross-sectional area. So we could have quite a bit of strength in a bolt like that. And we will find that bolts are surprisingly strong when we talk about their ultimate tensile strength. The second number here is the relationship between the yield strength and the ultimate tensile strength. So in this case, the second number is 0.9. That tells me that the yield strength is 90% of the ultimate tensile strength. And I can use this quite simple number to really get a calculation to say that since the ultimate tensile strength is 1,000, that 90% of that means that the yield strength of this bolt is 900 newtons per square millimeter. So if we take a look at how strong this bolt is, it's an M10 grade 10.9. That's a pretty small bolt. And the stress area is the smallest cross-sectional area of the bolt. We find that we measure that across at 8.7 millimeters. Little geometry tells us that is 60 square millimeters of cross-sectional area. That means that an M10 bolt can hold 60,000 newtons of force, or 13,500 pounds, which is over 6,100 kilograms. So that is a pretty incredible thing to think of. A small M10 bolt can pick up, probably 3 cars. That's a huge amount of available strength, and the goal of tightening is to generate a high and consistent amount of clamping force. That's why bolts work so well, is because they generate so much force and can squeeze things together so efficiently. We want to realize that when we go up in bolt strength, that we want to increase our torque. And the reason for it is that there would be no benefit, almost nothing at all, to increasing the bolt strength without increasing the torque. If you increase the bolt strength, you've increased its cost in almost every situation. It wouldn't make any sense to not go to a higher torque because the goal is to tighten to a high and consistent level. And as you can see, this is actually right out of our industrial tools catalog, commenting that this has approximately 62% of the ultimate tensile strength. So since the bolt strength goes up, the bolt torque goes up. And when we see a higher strength bolt, I would expect to see a higher torque associated with tightening because we want to get to a high level of clamping force. All right, in this section, we're going to talk about multi-bolt patterns. When we've got more than one bolt to tighten down, one approach to this is a multi-spindle. This is actually some of my favorite applications to work on, is because it's really interesting, tightening a large bolt pattern, the advantages we can give to that bolted joint, especially if we've got a lot of bolts to tighten all at once. You can tighten, 38 bolts down in 10 seconds or less and generate 500,000 pounds of clamping force. There are some distinct advantages to tightening with a multi-bolt pattern. We can really get a fast cycle time, we can get even torque distribution, and this improved clamping force. So let's break that down to a little more simple model. We got a 2-bolt pattern here, and we tighten the first bolt down. If we don't tighten these together, we get the situation where we might have low clamping force because there's interaction between these two fasteners, and this is what we call crosstalk. Crosstalk is when the clamping force of one screw interacts with the other one. A better way to tighten this would be to tighten with a multi-spindle assembly. So in this case, even though the bolts don't start off at the same level, we're running them down together and they're waiting for each other, so we can snug them both down, achieve that seating torque, and then we can synchronize the spindles and do a final tightening at the same value. This is going to produce a really even clamping force. If you don't have a multi-spindle assembly, you're going to have to go back and readdress the torque value of that first bolt. That first bolt is going to be affected by all the bolts around it. With a multi-spindle assembly, we can do a large number of bolts in a really short amount of time, and there's some real cost efficiencies to that. Let's talk about how accuracy affects the tightening process. We talked about applying torque to it, but there's going to be variation in the amount of torque that we apply to the joint. Typically, we see joints ranked in certain categories. This could be general at a 20% variation of torque. This could be a 10% tolerance for a critical joint, maybe a 5% tolerance for a safety critical joint, and that's going to look something like this, where we have a 50 newton meter target on a grade 8.8 bolt. If we have a general category of plus minus 20%, the results of our tightening process have to fit between 40 and 60 newton meters. A typical example like this with this large of a tolerance would be something that is pretty robust. There's other bolts around it that can support it. Maybe that's not as critical, and there's really no chance of injury or catastrophic failure or part function failure if this bolt didn't get the proper clamp loop. If we have a joint that's more quality critical, we find that oftentimes we see a tighter tolerance. And 10%, plus or minus 10%, is a pretty typical tolerance for say, an automotive application, where we got to fit between 45 newton meters and 55 newton meters. So this may also require that we use a transducer in the tool to monitor this tightening process. And so there's different types of tools that have different types of accuracy. When we're setting up a process in place, we want to make sure we're buying the right tool for the application so that we can achieve our process. And this is a general breakdown of the different types of power tools out there. On the top of the list, we've got our fixtured power tool. This tool is going to be at plus minus 2.5% accuracy. Down from there, we've got transducerized direct drive electric tools. This would be your right angle power tools at 5%, where you'd have an operator holding this tool. Then we've got some low reaction tooling like our LRT e-pulse and transducerized pulse tools. These use a different method of assembly, and they're going to have a reduced accuracy, but there's some advantages to using these that we find that are really good for operator ergonomics and really reducing the amount of torque that the operator has to withstand. So what you lose in accuracy, you gain in ergonomics. And there's trade-offs all in deciding what tool. Certainly cost is another factor at play here. But you can see that there's a range of things we can do to apply the right tool to meet the specification that's going to give us the right amount of clamping force at the end of the day. All right, we're going to talk about residual torque. And residual torque is a torque auditing process. So I want to be clear, when we talk about residual torque, we mean leftover torque. It's actually nice that the name is so descriptive. In our manufacturing process, we have a dynamic assembly tool. This is our torque that's on our drawing, 50 newton meters, and we want to apply that dynamically with a power tool. But what the residual torque is it's measuring after the fact the remaining torque in the joint. All right, I want to clarify some terms when we go through this. So we have our tightening tool here. We can measure that installation torque with an inline transducer. And then we're going to take a residual torque measurement in the tightening direction. In most cases, we're taking residual torque in the tightening direction. The only cases I would recommend you take it in the loosening direction is if you were trying to monitor, a locking mechanism and how functional that locking mechanism was. In most cases, what we're doing is using a tightening direction audit to understand how much torque is left in the joint. So this is a picture of two different traces. I want to be clear we're talking about the tightening torque that we put into this joint, and then the red curve here is after the fact. We're coming back and we're returning this joint in the tightening direction, and we're looking for the torque that is maintained in the joint. So we can see the scale and angle and how wide these are. We get a nice linear elastic tightening curve on the blue here where we hit our torque dynamically, and then after the fact we come back and we create this curve where we've tightened the bolt in the tightening direction, and we can see that breakover point. That's the point we want to look at and ask the question, what torque remains in the joint? So here's a zoomed in picture, a different application, but a good actual trace of an actual residual torque value. We have our static breakaway torque. This is the torque it takes to start it moving in the tightening direction. And then this point right here is what we call the residual torque. This is the best indication of the torque that's left in the joint, and it's the best indicator of what my dynamic torque was during the assembly. So the reason we're doing this process, this checking of the torque after it's being tightened, is to understand how much torque was applied in the direct application. So during our tightening process, we use this as an audit to verify how good our tightening process was by checking the residual torque. So we want to keep in mind what we're going to get out of this. This audit process of checking residual torque is really to make sure that the tool was set to the correct setting, that the right tool was run, right? Maybe we have multiple tools on our assembly line, and we want to make sure that the right tool is run on that joint. We want to make sure that the calibration is in a normal range. We want to make sure there's no damage to the tools or the cables or anything like that. And we want to make sure that there isn't any issues with the operator procedure. So the primary reason we do this residual torque process is to, on a regular basis, daily, weekly, to check the consistency of our process so that we don't have to calibrate tools every single day, which wouldn't really be feasible. So the residual torque process is a process that we put in place to audit the tightening. And the secondary reason we're doing this is to get an idea of the relaxation of the joint. So we could also pick up relaxation where the dynamic torque was correct, but something caused the joint to lose its clamp load, and that comes out in a residual torque check as well. We want to realize that both of those things are occurring when we're trying to problem solve a situation like this. All right, some things to remember. The tightening process is surprisingly complicated. I think we take it for granted. We have tightening torque that we put into this joint, and the goal is generating clamping force. So we have variation of friction that goes into play. We have joint relaxation, component failure, design concerns, production variation, tightening tool variation. And there's quite a few aspects of things that go into affecting the relationship between, what we program that tool to do and the actual clamping force that it generates that keeps the part together through its service life. This is a surprisingly complicated process, but if we take a look at the components that break down and what's important to the relationship between the tightening process and the clamping force we generate, we can really control a lot of these situations and do a good job of creating a robust assembly that's going to last through the service life of whatever product we're building. Some things to remember. Tight bolts perform best. In almost all cases, we want to tighten the bolt to a very high and very safe level. We don't want to yield the bolt or crack the parts in most situations there, but we want a high level of clamp load. The tighter the bolt, the better it's going to perform. Anything we do to control friction variation is going to dramatically improve the consistency of the clamping force that we create and the consistency of the part performance. But don't forget the goal is generating clamping force. So sometimes we get hung up on, making sure the tool is getting the right torque value, but the real thing that's keeping this joint together is the clamping force of the clamp load of that bolt. Elastic elongation, that stretch of the bolt where it stretches like a spring, that's what's going to keep the clamp load. So if we've got situations where we can't maintain the clamp load, increasing the elasticity is what's going to keep that thing together. So we need to have this balance of force and stretch. If we do that a good job on the design phase of the bolted joint, we're going to have a really good, robust joint that's going to be very long lasting. Angle monitoring is going to solve a ton of our joint quality issues. So if we put some simple things in place, we can make some really big advantages to our tightening process. Some small changes and a little bit of effort, we can really do a good job of creating a good assembly. And really, the right tool and the right process is critical to the success of the assembly. So we want to make sure that we're putting the right tool to the application and we're putting the right process in place, and we should have a really good, robust joint. And if we take all these things into consideration, we should be able to do a really good job when we go to assemble things in production. This has been the Torque Theory webinar. I hope this has been helpful for you. If you have any follow-up questions, feel free to reach out to your Atlas Copco representative, and thanks for watching.